In today's video, I'm going to talk about mantle hotspots. So you're probably looking at the map on page 5 of your Earth Science reference table. This is the tectonic plates map. In addition to having all of the plate boundaries marked and labeled, it also shows the location of mantle hotspots. So one of the most obvious hotspots to find is the Hawaii hotspot. And this is one of the first hotspots that was identified on the planet, and it's also one of the most widely studied. The Hawaiian hotspot is right in the middle of the Pacific plate. There's plenty of other hotspots that are also away from plate boundaries, right, such as the Tasman hotspot, the Canary hotspot, as well as the St. Helena hotspot. Not all hotspots are found away from plate boundaries in the ocean. Some are found on land, most notably the Yellowstone hotspot. All of the examples so far are away from plate boundaries, but the remaining hotspots are directly on plate boundaries. So the moral of the story is hotspots can occur just about anywhere. They can occur in the ocean, they can occur on land, they can also occur in the middle of a plate or directly on top of a plate boundary. Right, so they can be found absolutely anywhere. A common readings question is to identify a specific hotspot given a set of coordinates, latitude and longitude. So how do we start here? We're given a latitude of 20 degrees north. So first you have to identify the equator. That's our 0 line for latitude. And we want to be above this because we're in the northern hemisphere. So we're going to be somewhere along the 20 degrees north line. So identified by this blue line across the map. And then we're at 158 degrees west. So first we have to identify the prime meridian. That's our 0 line for longitude. We're going to go westward from there. The way I like to remember the Western Hemisphere is by identifying where North America and South America are. Both of these continents are in the Western Hemisphere. So 158 degrees west is just before 160 degrees west. We find out where do these two lines intersect, and we're talking about the Hawaii hotspot. So what are hotspots? These are volcanic regions that are fed by underlying mantle that is anomalously hot. So this mantle, for some reason, is hotter than the mantle around it. The kind of cool thing about hotspots is that they don't move, but the tectonic plates above them do move. So you'll end up with a chain of volcanoes like the one that you see in the animation. All right, so you can see the volcanoes are forming directly above the hotspot location, and then as they move away, they slowly get smaller and smaller as they weather and erode back into the ocean. This can actually be quite useful. So we can actually figure out past plate motions based on the age dates of the volcanoes. All we have to do is draw an arrow. That arrow points from the youngest material, that's where the hotspot is located, and it points towards the oldest volcanoes. And that tells us this plate is moving to the upper left of this page. If I was using a cardinal direction, this would be towards the northwest. So practice problem number 1. As always, feel free to pause the video here and try this out for yourself. We're going to put a box around what we're looking for. We're going to underline any key information included in the problem. So we're looking for the ages of volcanoes B and D. And then the information that we know is embedded within the diagram that's provided. We know that volcano C is 8 million years old. We know that volcano A is right above the hotspot. So we can infer that the age of this volcano is 0 million years old. It's brand spanking new. Right, so if this is 0, C is 8, B must be between 0 million years old and 8 million years old. And D is further away from the hotspot than C, so D must be the oldest. Choice number 1 says B is 5 million years old. That's between 0 and 8. And D is 12 million years old, which is older than 8 million. Choice 1 is the correct answer. As you move farther away from the hotspot, the volcanoes will get older and older and older. Here we have practice problem number 2. Again, feel free to pause the video and try this for yourself. So we want to know what compass direction the North American plate moved during the last 16 million years. And again, the information that we have is contained within the diagram. And so we know we have the age pattern of calderas. Those are volcanic collapse features. And we know that the youngest volcano is towards the northeast at 0.63 million years old. And the oldest caldera is 16 million years old in the southwest of the map. So now we just draw an arrow from the youngest feature towards the oldest feature. And that will give us the direction of plate motion. So we compare this to the north arrow, where you can draw yourself a nice compass rose. And this arrow would go in between south and west, indicating that the North American plate has moved towards the southwest over the past 16 million years. Hope you enjoyed this video. If you have any comments or suggestions, please leave them below.